Hello guys, welcome to another video. Alright, in today's session, we'll be looking at how to demystify this magnetism question. Okay, now there's a challenge now that I was given was that I should prove the equation for the magnitude of magnetic field of a circular, that's in a circular coil. So this video is not meant to take our time as far as I'm concerned, but because of the proof, okay, so it's important we see how the magnetic field for a circular coil, okay, why it is different from that of a straight wire or a straight conductor carrying current. Okay, so now let's have our solution. Now, the first thing is for those of us that we find love with this aspect of physics, okay, that's the magnetism, electromagnetic induction, nuclear physics, and the rest. Now, I want to believe that we all know that experimentally it was found that the magnetic induction arising from a charge, okay, let me draw the diagram. Yeah, the magnetic induction arising from a charge. Let's say we have a charge. This is the charge arising from a charge, okay, moving with velocity v, okay, at a distance r, away from the charge. Okay, now let's say the vector for r is what we have as r caret. Okay, now to the point where the magnetic field is found. So let's say the magnetic field is found somewhere here. Okay, so now in this case, now the inclination between r and v will be theta. So the magnitude of the magnetic field will be proportional to the product of the electric charge and the velocity of the charge. That's the velocity of the moving charge. Then, and the sine of angle between the velocity and the distance away from the charge. All right, so then over the what? The distance away from the charge raised to the power of what? Raised to the power of 2. Now, when we replace the proportionality sign with equality sign, then we are going to insert a constant. That's a constant factor. So the constant factor in this case, just like the case of Coulomb's law of electrostatics, where we have the electrostatic force of attraction between 2 point charges. You know, attraction is when we have unlike charges. Okay, so when we have unlike charges, you know, they will attract each other. Why? Repulsion will be when we have like charges. Okay, that means when we have two like charges or similar charges of electrification, they will repel each other. So the electrostatic force of attraction or repulsion between 2 point charges will be proportional to the product of their magnitude. That's the magnitude of the corresponding charges. Okay, and inverse proportional to the square of the distance separating the two charges. Now let's say we have two charges. Okay, we have two charges. Let's say we have one is positive, which is Q1, and the other one is what? Negative, and that's Q2. And both charges are separated at a distance r apart in an homogeneous and isotopic medium. So the force due to Q1, that's the force on Q1 due to Q2, would be what we have as F proportional to what? Q1 multiplied by Q2, then at a distance r apart. So then it will now be what? Inversely proportional to the square of the distance of separation between the two charges. So, and this is given by what? By the Coulomb's law. All right, so in this case, we're going to have what we call the Bauer-Savart law. You know, now, we know that the first significant relationship between current and magnetic field was discovered by Oersted, yeah, in the year 1820. You know, Oersted found that a magnetized needle, okay, set itself at right angle to a straight wire when a steady current is passing through the wire. Yes, that's according to Oersted. Now, in the same year, we then have these two guys. I mean, these two men. You know, they came together. That is Biot and Savart. You know, the Biot and Savart law. We have the Biot and Savart law. So they formulated an equation. That's a mathematical equation for the what? For the magnetic field due to a single current element. Okay, so due to a single current element. So in this case, we're going to employ the use of Biot-Savart law. Biot-Savart law. So now, so we have B proportional to QV sine theta over R squared. So we can then write this to be equals to permeability of free space over 4 pi, then multiply by, we can have Q, then V R over R to the square. Okay, that is R to the square, that is R carried, okay, represents sine theta. Okay, then we have R to the square. Don't forget that this R is the what? Is the vector of R, which points away from the charge to the point where the magnetic field is formed. Okay, now in one of my videos, I explained that to, to calculate the magnetic field of a straight wire carrying current, okay, we have it to be B equals to permeability of free space multiplied by current I over what? 2 pi R. This is for a straight wire carrying current or a straight conductor carrying current. Then we also have for solenoid. Okay, the magnetic field of a solenoid is permeability of free space multiplied by number of turns times the current over what? The length of the what? Of the long cylindrical coil, which is what is known as solenoid. Then also we have the magnetic field of a circular coil, which is this was the formula, okay, I used in solving a particular, that's a question in one of my videos. So we have this multiplied by, so I over what? 2R. So this is the magnetic field through n turns of a circular coil. Then we can also have magnetic field through 1 turn of a circular coil, which we are going to use in this case because we want to calculate the magnitude of B at the center and the magnetic dipole moment. All right, so now we can see here that we have permeability of free space n times I over 2R. Now, one of my professor asked me that I omitted pi in that solution, and I already explained to him why pi was not omitted. That we have permeability of free space to be n multiplied by I over 2R. Okay, that is permeability of free space times n multiplied by I over 2R is what we have for the magnetic field of a coil. Okay, so now talking about the circular coil, according to Biot and Savart law, I said the Biot and Savart law, okay, the Biot and Savart law is that law that talks about the formulation of a mathematical equation for finding the magnitude of the magnetic field due to a single current element. So we're going to have here that for a circular coil, now for a circular coil, let's say we have this is a circular coil, okay. Now this is the radius of the circular coil. Now we have the distance away from the point where, from the point where from the charge to the point, or from the magnetic field to the point, that's to the point where the magnetic field is formed. Okay, now then we have the what? We have what we call the radar. Okay, so this is the angle which the you know the vector for current makes with the what? With the reader. So this is the vector for current for a single current. That's this represents vector, okay, for a single current. Vector for a single current, which is perpendicular to the what? To the reader. Okay, now, so in this case, now, the magnitude of the magnitude of the magnitude of the magnetic field, okay, the magnetic field of the elemental material. We have the elemental material. The magnetic field of the elemental material is dB, which makes an angle of theta alpha, this angle with the what? With the horizontal. So according to Biot and Zavart law, the magnitude of the elemental magnetic field would be what we have here as permeability of free space over 4 pi, then multiply by I dl over r to the square. Now, let me quickly explain where this IDL came from. Okay, now the electric charge, crossing the cross section per second of the circular coil, the electric charge crossing the cross section of the circular coil per second is what we have as electric current. And that will be when we have density times V times A. Now, so by the time, if you now multiply this equation, if you multiply this current equation by the what? The the vector for the current, okay, in the coil. So we are going to have IDL to be equals to, this, then DL times what? Times A. Now, the total current in the straight wire of length DL will now be what we have here as now. Q is the density times V times what? No, density times A times the what? The vector for the single current. So this represents the total current. This represents the total current in the straight wire. The total current in the straight wire of length DL. This is very important. Now, I already skipped some parts because the proof is it's not long anyway, but I already skipped some parts in this case. But what is important here is we have Q to be this, so which means when we represent this A and then DL with Q, so we then have IDL to be equals to QV. Can you see? We have QV in this case, QV sine theta over R squared. So the QV we have here, over R. Now we have QV sine theta over R squared. So let's say we consider that the angle is 90 degrees. Sine of 90 degrees will be what? 1. So we can then have QV, okay, QV R carried over what? R squared. But here we have IDL. Okay, so this IDL, okay, represents what we have here. That is QV, then R carried. So in this case, so we have the magnitude of the elemental, that's the magnetic field of the elemental material. This is it. Okay, so then we know that from the concept of integration, when we write B equals to the integral of dB, when we integrate with respect to B, we're going to have B. Now, the magnetic field of the elemental material is what we have here as this equation. So we are going to what? We are going to insert this into this equation. So with that, we are replacing dB with what? With this. So we then have permeability, okay, of free space over 4 pi multiplied by I, okay, dl over what? Over R squared. Then cos alpha. That's because of the vector, the R vector. All right, cos alpha. Now let's go back to this diagram. I said this is for a circular coil. We have the magnetic field along the axis of a circular coil. So in this case, so we then have that. Now, what is cos alpha? We are considering this angle. This is the adjacent. This is the what? Hypotenuse. So we know that cos alpha will be the adjacent, which is R. That's a big R over what? The distance away from the charge to the point where the magnetic field is formed. Now, then we know that R, okay, if I'm using Pythagoras rule, okay, R would be the square root of R squared plus X squared, okay, plus X squared. That's R. So we are going to what? We're going to plug it into this equation. Then also let's note this. The integral of the element, that's the integral of the vector for the single current, okay, is equals to the circumference of the circular coil, which is 2 pi r. Okay, so now, so we have this to plug in, we have this to plug into the equation, into this equation, and we also have this to plug into the equation, and also this. All right, so we then have B B to be equals to permeability of free space over 4 pi. Okay, then multiply by current I, then dl. Remember I said integral, let's do it this way. Now, cos alpha, we have cos alpha to be what? The big R over what? The small r. Okay, then multiply by, now, we know that we also have integral of dl, okay, the length in the what? In the length of the straight wire. So we have integral of dl. Okay, so this becomes B equals to permeability of free space over 4 pi multiplied by current I. So we have the big R over the square root of big R squared plus X squared. Okay, then multiply by 2 pi R. Okay, so 2 pi out of 4 pi, that will be what? 2. Okay, then, so now in this case, then we now have R squared. So now remember, this is what? This is raised to the power of what? This is raised to the power of 2. Then we have big R over small r. So then multiply by r squared. So we have r squared to be r squared. This is the big R squared plus x squared. Okay, raised to the power of what? Raised to the power of 2. Raised to the power of 2. So in this case, we're going to have magnitude of the magnetic field intensity, okay, to be permeability of free space. So R times R, that will be R squared, okay, then times I. So we have R squared, IR squared over 2. Now, like I said, the square of root R squared plus X squared will be R squared plus X squared. So when we multiply by this other guy, so we're going to have R squared plus X squared, okay, raised to the what? 3 over 2. Raised to the 3 over 2. Yes, because the square root of r squared plus x squared, that will be r squared plus rx squared. Now we have r squared plus x squared raised to the what? To the power of 3 upon 2. All right. Now, at the center of the coil, we are given here that we should calculate the magnitude of B at the center of the coil. Now, the center, at the center of the coil, okay, x will be equals to 0, so that B will be equals to permeability of free space times I, then multiply by r squared over 2 bracket r squared, okay, raised to the what? 3 over what? 2. 3 over 2, okay? Because when we set x equals to 0, so this will reduce to r squared, so that this becomes B equals to permeability of free space times I, which is the current, then multiply by r squared, okay, over 2. This will cancel out, so we'll be left with what? R raised to the power of 3. So r squared out of what? R raised to the power of 3, that will be 1r. So we then have B equals to permeability of free space times I, okay, times I all over 2r. Now, can we now see that we now have the magnetic field, okay, in a coil? That is, in a coil. That's a magnetic field through 1 turn of a coil, of a circular coil. This is the magnetic field, okay, through 1 turn of a circular coil. And then we also have that of n turns of a circular coil to be permeability of free space, then n times I over what? Over 2r. This one is through n turns of a circular coil. Yes, so this is the formula we're going to use to solve this problem. Now, the first thing we need to find out is the current, because we are given the radius, we are given frequency, but we are not given the current. So to calculate the current, because we know that current is the charge flow per second, so we are going to have the current, okay, to be, now, electron. We know that the charge on electron is 1.602 times 10 raised to the power of negative 19 coulomb. So we have 1.602 times 10 raised to the power of negative 19, then multiply by, so we then have the frequency, which is 6 0.8, okay, times 10 raised to the power of 15. So the unit of this will be in what? Amperes. So let's get the value for current. So we have 1.602 multiplied by 6.8. Okay, that will be 10.89. So we have I equals to 10.89 times 10 raised to the power of -4. So when we move the decimal points, so the current will be 1.089 times 10 raised to the power of -3. So this is the magnitude of the current. So we need this. That's why we must calculate it. Okay, so we must calculate the value for I. So now we know the value for I, so we're going to plug in the value for I into this equation. Now don't forget that for permeability of free space, permeability of free space is a constant. Okay, and the magnitude for the magnitude of permeability of free space is 4 pi times 10 raised to the power of -7 Tesla per meter. So we're going to use B. So the first thing we want to calculate, okay, let's say from here. So we now have B equals to 4 pi times 10 raised to the power of -7 multiplied by 1.089 times 10 raised to the power of -3 all over 2 multiplied by the radius. The radius is 5.1. Okay, 5.1 times 10 raised to the power of -11. All right, so what is 1.089? Okay, 1.089 multiplied by the value of pi, then multiply by 4. Okay, so that would be 13. We have B to be 13.687, then times 10 raised to the power of -10 over, this will be 10.2 times 10 raised to the power of -11. Yeah, because 2 multiplied by 5.1 is 10.2. Okay, so let's divide this value by 10.2. That's 10.2. All right, and that will be, the value of B would be 1.342. Okay, now then we're going to add the what's it called? We're going to add the powers because this is -11, so it will be added to 10. That will be 1. So we multiply this by 10 raised to the power of 1. So the magnitude of B would be 13.42 Tesla. This is the magnitude of B, and that's the first question. That's the first question. Now, the second question is about magnetic dipole moment. What is magnetic dipole moment? Magnetic dipole moment measures the product of the pole strength and the distance of separation between the poles, or it also measures the strength and the orientation of the dipole, okay, when they are separated by a small distance. So magnetic dipole, okay, we have our magnetic dipole to be NAI. Okay, yeah, that's NAI. So where A is the cross-sectional area, where A is the what? Cross-sectional area. So the area would be pi times r squared. So which means it will be pi multiplied by the radius, which is 5.1 times 10 raised to the power of -11 squared. Okay, so the number of turns, remember I said what we found here is the magnetic field through one turn of the coil. Why this is when we have magnetic field through n turns of the coil. So we are going to bring this here. So we have the magnetic dipole to be 1 multiplied by the value of currents, which is 1.089, okay, multiplied by 10 raised to the power of -3, multiplied by this guy, pi times 5.1 times 10 raised to the power of -11 all squared. All right, so now 5.1 square multiplied by 1.089. Okay, that would be, this would be equals to 28.325. Okay, multiplied by, we have 1.089 multiplied by 5.1 raised to the power of 2. Okay, so we found this, then multiply by 3.142, which is the value of pi. Okay, so this is going to be 8 8.997. Okay, times 10 raised to the power of negative 3. Now, 10 raised to the power of negative 11 raised to the power of 2. That will be 10 raised to the power of minus 22. The unit of this, since we have current, sorry, area and current, so it will be ampere square meter square. So this will combine so that magnetic dipole moment will be 8.89, okay, times 10 raised to the power of negative 25 ampere meters square. And this is the magnetic dipole moment. The noblest pleasure is the joy of understanding. Bye bye.